welcome to all of you in the next class of this course. So, first let us summarize what we have done in the last lecture. In the last lecture we have seen couple of disadvantage of the Fourier transform, and so remove some of the disadvantage of Fourier transform we defined Gabor transform. The definition of the Gabor transform which we looked at was this. Okay. This is the way we defined Gabor transform in the last lecture. So, if we wanted to write this in the form of a inner product, we can write F into W. Okay. So, now where W will be function e to the power I omega x E alpha x minus b. This is a real function, so we do not need to bother about the complex conjugates here. Okay, so basically we have seen that we are localizing Fourier transform if you look at this definition more carefully, which we have written f inner product with function w, and w is a window function. So, it is localizing function f. That is why when we wanted to analyze the function in the time domain, this will be called time window. Now, if I use Parseval relations which we have seen in the last lecture also, then this will become this. So, you can define this as equal to f hat into h, where h will be 1 over 2 pi w hat. Now, what is w hat? W hat you can look at from here, that will be this function, or let us say what we are defining here, e to the power minus alpha into omega square. This is a inner product of this. So, that is we are defining w hat. Okay. Okay. So, what we see that Fourier transform of Gaussian is Gaussian itself with different with that I have mentioned in the my last lecture itself. So, we can also localize function in the frequency domain, because h is also a window function, that is also in the form of a Gaussian. Okay. We can look at the signal in time window as well as in the frequency domain, and we need only localized information, because we are localizing the signal with the help of this window function w and h. That was the idea behind Gabor transform. So, in this course you must have heard another kind of a transform as well, like Laplace transform, Fourier transform. In fact, I have also discussed Gabor transform, etc. So, Gabor transform is also one kind of a integral transform which is used in time frequency analysis very often to remove some of the disadvantages of Fourier transform. So, this is the point where I left in the last lecture, and I said that now I will define window Fourier transform. So, in window Fourier transform, the idea is instead of using this as a Gaussian, we are using some general window functions. So, we are denoting with this w. Okay, so, the idea behind window transform is that instead of using Gaussian here, we are using any other general window function. So, with that idea, let me define what is window Fourier transform in the next page, let us say. So, again f x e to the power I omega x w1 x minus b into dx. So, again we can write down this as a this way, where w is e to the power I omega w1 x minus b. Okay. So, and similarly we can write down f hat into h, where h is 1 over 2 pi w hat. Okay. So, what will be the w hat here? That you could calculate from here. Okay. So, again this will be e to the power I eta minus omega, and this will become w1 hat eta minus omega. So, that will be the idea behind this w1 hat. If you look at previous page, here also it will be eta minus omega b. Okay, just eta minus omega b. So, this is the idea behind window Fourier transform. Okay. It is also called short time Fourier transform. Short time Fourier transform. Okay. So, here if you have analyzed the concept, what is the assumption I should make on w1 and w hat? W1 hat, the assumption again I am using on w and w hat or w1 and w1 hat is that it should be a window function. Both should be a window function. So, in a nutshell, w1 and w1, these should be window functions to define window Fourier transform. Okay. Because only then we can localize the function in time domain as well as in frequency domain, which was the we were not able to localize this function in a Fourier transform, and with the help of a Gabor transform we are able to localize. That is the idea behind. So, if you look at more carefully, Gabor transform is a special case of a window Fourier transform where W1 is equal to the Gaussian function itself. Okay. So, now what will be the time window? If you look at in the previous page also, what should be my time window? If you look at this, the center of the Gaussian is 0, we all know. So, what will be the center of this E alpha x minus b? It will be shifted Gaussian. So, just for your clarity, I am again writing this W hat which can also be written in the following way. Okay. This is E 1 by 4 alpha, that is what we are writing, because it will help us in defining the area of the time frequency window. That is why I have rewritten this in the following form. So, I was talking that okay, the center of the Gaussian is 0 and radius, let us say we are denoting by this alpha, though this will be assignment question that this will be equal to under root alpha for alpha greater than 0, but that we will anyway prove later. So, if center is origin and radius is this, what will be the time window? Time window will be b minus this into b plus under root alpha. Okay. And that was the reason I have written this W hat in the following form, so that you can directly calculate what will be the frequency window. So, this W hat, of course, this is a function of eta that you could write down here. So, this will be omega minus 1 by 2 under root alpha omega plus 1 by 2 under root alpha. Okay. So, this will be the frequency window. And this will be the time window. Clear? How we are calculating the time window and frequency window? Okay. And what will be the width of time window? 2 under root alpha. What will be the width of frequency window? That you could also calculate. So, if you look at the product of time window and frequency window, that is 2, that you can calculate. So, the area of this time frequency window is 2. Now, similarly, we are defining what will be the time window with respect to window Fourier transform. Time window will be x star plus b minus del omega 1 x star plus b plus del omega 1, because then x star is the center of W1. In the Gaussian case it was 0, that is why we were not writing this. Okay. But in this case this is a general window function. So, let us define x star is the center of W1, then this is W1 x minus v. So, center will become this, and we are assuming that del omega 1 is the radius of this function W1. Based on that concept we are defining time window. Now, let us say what will be the frequency window. Frequency window will become omega star, because that you could see from here, plus omega minus del omega 1 hat into omega star plus omega plus del W hat. Okay. So, here you could see what is W star. W star is the center of W1 hat. So, shifted, this is a shifted. So, then this will become the center. This way we are defining the frequency window. So, now if you look at what will be the area of this time frequency window? Area of time frequency window will become area of two del omega 1 2, because this will be the width of time window 2, this will be the width of frequency window. So, this will be the area of a time frequency window, while in the case of a time frequency window which corresponds to Gabor transform, the area was 2, we have just calculated. So, there is one more thing which this principle tells us, that is called uncertainty principle. So, this is one kind of a principle which tells us that you cannot achieve a window smaller than Gabor window. So, Gabor window is the smallest window which one could achieve. The proof of this principle is also given in the book of Charles Quechu, but I am stating this without proof. So, basically it means that area of any general time frequency window is this. So, which is then this will always be greater than 2, okay, because so means 2 is the area of a time frequency window which is corresponds to the Gabor window, and that is the smallest window one could achieve, and this equality will be attained if and only if W1 will be a Gaussian function. That is what we have seen also. So, whatever I have done here to support that argument theorems, and I have also plotted that thing. Let me show that figure to you. So, this figure you could look at more carefully. So, this is, you could say, time window where the under root alpha is the radius, total width will be 2 under root alpha, and this is the frequency in the frequency domain 1 by 2 under root alpha, and the area of this time frequency window is 2, which is a constant. So, whatever I have said graphically you could look at that thing with the help of following figure, that this is corresponds to time domain, this is corresponds to frequency domain. So, area is constant, which we have just proved also. This is just a graphical version of the same thing which I have said there mathematically. So, now this gives you a complete picture how you could look at any function with the help of a time frequency domain. You can look at the function in time domain as well and in the frequency domain as well by using the local information of the function, because this the window function which we are using are localized function or window function. Windows are always localized functions. So, now let me give you the how this integral transforms are evolved with respect to analyzing the function. First we were defining Fourier transform, then we were defining window Fourier transform, or particular form of window Fourier transform is Gabor transform, and then later on we will define one of the most promising wavelet transform, which is also a integral transform. When I will define the wavelet transform, I will show you what is the drawback of window Fourier transform which is removed in wavelet transform. So, that is also one of the integral transform, but it has advantages over window Fourier transform, and that is how it is evolved. But before defining the wavelet transform, I have to define the concept of a what is wavelet. Okay. So, for that reason we are changing our topic and now we are defining what is wavelet. That okay. Okay. So, wavelet is basically initially discovered by two scientists, Grossman and Morlet. Okay. And both of them were physicists, French physicists. It is not a legacy of this mathematicians. This is the concept which was discovered by physicists, and when it was invented, it was invented with the name of Ondy late. Later on it was converted to the English by saying Ondy means wave and let means, as we all understand what is the meaning of let in English, small wave. Okay. So, that's how it is invented. Later on it becomes very popular after doing a complete mathematical analysis by many scientists like Grossman, Morlet, again Daubechies, Stromberg, etc. Okay. So, now to define wavelet in a very layman language, what kind of functions you can call it as a wavelet, I am giving two properties which any wavelet should satisfy. Okay. So, the wavelets most of the time it is denoted by function psi x in a one dimensional if x belongs to R. Okay. So, which kind of functions you can call it as a wavelet? The function and its Fourier transform should be localized. Okay. There is a difference between localized function and compactly supported function that you should look at. Gaussian is localized function, but it is not a compactly supported function. So, please do not misunderstood that localized and compactly supported functions are can be interchanged. Okay. So, the function and its Fourier transform should be localized. That is the first assumption if you are calling any function as a wavelet. The another assumption is psi x dx should be 0. It means waving above and below the x axis. So, these are the two property which is you could call must to define a wavelet. There are other properties also one could see in any wavelet, but those properties are desirable for some particular applications or for the computational efficiency. So, these two properties are basic and other properties are desirable for particular applications or for computational efficiency. Okay. So, because later on you will see many more properties which is suited for some particular applications or for computational efficiency. So, now if I ask you two functions which we have used in Fourier transform and Gabor transform, one of the function is Gaussian and another is e to the power I omega x that we were doing in Fourier transform. So, which is basically a combination of sine and cosine. So, if I ask you to look at the Gaussian function, the function and its Fourier transform is localized. So, first property is satisfied, but second is not satisfied for a Gaussian function. That is why you cannot call Gaussian as a wavelet. Clear? The next function you could take, because sine function satisfy this property, but its sine is not a localized function. So, that is why you cannot call it sin x also as a wavelet. So, I have given two examples of a functions which are not satisfying these property, and that is why we are not calling them as a wavelet. So, now the next question comes, can you tell me any function which will satisfy these two property? Of course, if graphically I define this kind of a functions. Okay. So, let us say this is 0, this is half, this is 1. So, in 0 to half it is positive, in half to 1 it is negative. So, of course, it will satisfy the second property, and it is a compactly supported function. So, every compactly supported function is localized. So, then it is also satisfying the first property. So, these kind of functions you could call it as a wavelet. Of course, this is I have given you the example, but how to construct a wavelet, that itself is a non-trivial task. So, for that reason, how to construct wavelet mathematically, we are going to define the main theory of the wavelet, that is called multi-resolution analysis. Okay. Multi, or in a short form it is called MRA, multi-resolution analysis. Initially, multi-resolution analysis was invented by Stephen Mallat and Weismeier. Okay. They are the one who discovered multi-resolution analysis for the construction of the wavelet mathematically, how to construct wavelet mathematically. So, basically it is this theory is also called heart of the wavelet theory. What is the goal of this MRA? The goal of MRA is to express any arbitrary function, okay, which belongs to this space L2x, where x is any manifold, or just for simplicity, as far as this course is concerned, we are taking x is equal to r. So, basically we wanted to analyze the function which is a square integrable function over the real line. So, we want to approximate this function with the help of multi-resolution approximation spaces. So, you could say multi-resolution analysis is defined with respect to two spaces, and they are called multi-resolution approximation spaces. What is the symbol of those spaces, that I am defining later on. So, but multi-resolution analysis is explained with respect to two spaces which are called multi-resolution spaces. Okay. One of the space I am defining Vj and another space I am defining Wj. So, initially we will concentrate on this space, later on we will also bring this space. Okay. So, what is the goal of MRA? The goal of MRA is to decompose the whole function, okay, which belongs to this space into a subspace at the different levels. Okay. The goal of MRA is to decompose the function f belongs to into subspaces at different scales. What is the meaning of this different scales? I am coming to that, and because of that meaning different scales, it is called multi-resolution. So, these are synonyms you could understand, multi-resolution or multi-scales. Resolutions are basically synonyms of the scale, okay. Subspaces at different space. So, as I have already said that first I will focus on Vj and then I will focus on Wj. Okay. So, what are Vj's? They are closed subspaces of L to R. So, Vj are closed subspaces of L to R. These spaces are increasing. It means Vj will always be contained in Vj plus 1. So, these subspaces are in an increasing direction, it behaves like this. Vj is contained in Vj plus 1, and later on this property will be called as a nestedness property of the spaces. Now, if we go in the increasing direction of the J, we will have the completeness axioms L to R. Okay. So, basically what is the meaning? If at J tends to infinitive, basically this will Vj will tends to L to R, and if J is decreasing, means J tends to minus infinitive. So, with that property we are calling it as intersection of Vj is 0, null set. Okay. So, that is how these approximation spaces will behave in the increasing direction of J and in the decreasing direction of the J. And so, basically it means if PVJF is the projection of f on Vj, sorry, it should be Vj. So, I have when I was doing the mathematical foundation, I have already said what is the projection. So, I do not need to recall that it again. So, if Pj is the projection of f on Vj, so then PVJ f will tends to f when? As J tends to infinite. Okay, that is what we have just said. In the if J tends to infinitive, Vj will be like L to R, and because of that reason this completeness axioms is satisfied. Okay. So, now when we are moving from space Vj to Vj plus 1, how we are moving? So, for that reason we are defining one another property which is called invariance to dilation. So, if f belongs to Vj, if and only if belongs to Vj plus 1. Okay. So, all the dilated element of the Vj are in Vj plus 1, and now what is the dilation factor we are taking? The dilation factor is 2. Okay. So, this is called dilation, invariance to dilation, invariance to dilation. Okay. What is the other property? If f dot belongs to Vj, if and only if f dot minus k will also belongs to Vj. This property is called invariance to translation. Okay. Invariance to translation, and this is invariance to dilation. So, one of the natural question which can come to your mind, that why I am using only 2, I can use any other integer which it's like 3, 4. So, what should be your answer for that? Yes, you could use any other dilation parameter also, but we are using 2 for computational efficiency, which you will see later on what kind of computational efficiency we are talking. The next thing is invariance to translation. So, if you look at these two property, my question to you is that when you were defining, what were the Fourier basis function? E to the power I omega x. So, at that time also, if you remember, I said basically whole L2 0 to 2 pi space was generated by one function, by dilation of a one function. Okay. If you remember, I said, but in case of a L2R, it is generated by which function? It cannot be, here we are using dilation, because when we are defining wavelet, we are saying it should be localized. So, if we wanted to cover the entire space with the help of a localized function, so of course translation will also be needed. Okay. While in this case we are not having any translation things, but to define a wavelet we need two concepts: invariance to dilation, invariance to translation. Translation property was not in Fourier basis function, but dilation, which you see here, because we were dilating a single sin x, sin 2x, sin 3x, that is a dilation of a one single function sin x. Okay. So, these are some of the background I have made to define MRA more mathematically in the form of a assumption. If you see any book on the wavelet, MRA are always explained with the help of assumptions. And what are those assumptions? Those assumptions are basically whatever I have said in this page or in the previous place here and there. Now, I will collect all of them in a, to put in a more mathematical form, and they will be called MRA assumptions. Okay. That I will do in the my next lecture. So, thank you very much.